This is Taylor and Maclaurin Power Series, day number 1. This is some fun stuff, and honestly, it's cool. We only have 5 lessons, and we're going to take a test. And actually, we're going to squeeze those, let's see, Thursday, Friday, Monday, Tuesday. Yeah, so we're going to take a test next Thursday, and honestly, I think that this test, if you thought alternating series test was difficult, which I think most did, we're going to move on to Taylor, and it's going to be a lot easier. I think that the class average on the test will be a lot higher. So here's basically what we're about to do. Okay, so what a power series is it's a representation of any function, and we can make it as simple or complicated as we want to based on the power of the power series. So this represents a degree 0 polynomial, so it's just a constant, right? This would be a degree 1 polynomial, which just means it'd be a line, a representation of a function using a line, and then a quadratic. So if I wanted to, let's say, try to model this function, which I don't know what the function is, but if I modeled it with a 0 degree polynomial, right, it'd just be a constant value. Let's say a sub 0, right? It'd just be a line. Is that a pretty good representation of that polynomial or that function? No, it's not. It only has really a couple things in common. The most important one is this, is that both of them have this point in common. Okay. Okay, so then let's take it to the next level and let's find a first degree polynomial that would represent this function. Well, what would be true is that a first degree polynomial that has the same slope at that point and goes through that point would be a step up, right? So it would be a sub 0 plus some value a sub 1 times x. That value a sub 1 would be the derivative of the function at 0. Right, and then we could take it and go another level further. Right? So we go to a quadratic. So it'd be a sub 0 plus a1 times x plus some a2 times x squared. Well, what would that graph look like? Well, it would start to look like the red function in this small area close to 0. And as we take the higher order derivatives and give it the same derivative as f of x, as we increase that to a 4th, 5th, 6th degree polynomial, etc., it'll actually start to model and look exactly like the original function did. It will, as we go higher order, let's say we go up to like a 10th degree polynomial that has the same derivatives all the way along. What would an x to the 10th type polynomial, I'm not going to write all the other terms, but what would the end behavior on that be? Down and down or up and up? Up and up. So what it would do is it'd look kind of like the function everywhere and then tail off with its end behavior. It starts to look a lot like that polynomial or that function. Okay, so an 8th degree polynomial would look very similar, but it probably wouldn't fit the function for quite as long, but it'd still have the same end behavior. What would a 7th degree polynomial look like? Well, that has a different end behavior. So it would go up to the right, down to the left. So that polynomial might look like this, up to the right and down to the left. So it would start to fit that function as we get a larger order to that derivative around 0. Okay, so that's the goal. So let's do an example. Let's say we're given some clues. We know that q2 of 0, what does this 2 mean? What would the degree of the polynomial be? Yeah, so it'd be a quadratic. We're going to fit a quadratic to this information. Okay, so q of x, or q2 of x, is b sub 0 plus b sub 1 times x plus b sub 2 times x squared. I don't know exactly what b sub 1 and b sub 2 are yet, but I will soon. So let's say I take q2 of 0. B sub 0 would still be the same, but what happens to the rest of these terms? Yeah, they turn into zeros. So I know that b sub 0 is equal to q2 of 0. Well, what is b sub 0 equal to then? 1. So in my polynomial, which I'm about to form, q2 of x, the linear term would be 1, okay? Now let's do this. Let's go back to the original. Now let's take its derivative. What would the derivative of q2 of x be? Well, b sub 0 is a constant, so that'd go away. What would the derivative of that be? b1. And what would the derivative of this be? Yeah, b2, b2 of x, right, times x. So what would q2 prime of 0 be? b1. So b1 equals -7. Okay, so now I got the second portion of my, remember, that's b1, so that's attached to x. And now I can do the same thing for the second derivative. I'm going to take the first derivative and take the derivative of that. What would the derivative of the derivative be? It would equal 2b2. Okay, what was b2 equal to? Right, so this was 14. 2b2s equals 14, therefore b2 equals 7. So I've now been able to come up with a polynomial representation of these characteristics. The function that would fit this the best would be 1 minus 7x plus 7x squared. Okay, so if I took the first derivative and plugged in 0, I'd get what I got, right? Etc. So that would be a polynomial representation. This function, I don't know what it is, right? I don't know what this thing is, but that would fit it pretty well out to a quadratic term. This is really important, but isn't this kind of curious? q2 of 0 equals 1. q2 prime of 0 equals 1. And q2 double prime of 0 equals 1. What is the only function we know whose derivative always stays the same? E to the x, right? The initial reaction is, oh, it's a line, it's got a slope of 1. But if you have a line, it doesn't have a second derivative, right? So this function y equals e to the x has an infinite number of derivatives. So we could go out as many terms as we want. Now let's do the work on this. So if q2 of x equals b sub 0 plus b sub 1x plus b sub 2x squared, what would q of 0 equal? q2 of 0 would equal b sub 0, right? Because everything else cancels. These two would cancel. So b sub 0 equals 1. Okay, so q, the second degree representation of whatever this function is, which we know is e to the x, is 1. That's our first term. Let's take the derivative now. Derivative of that is going to be what we got before, which would be b1 plus 2b2 of x. What if I plugged a 0 in there? What would I get? b1. What is b1 equal to then? 1. Okay, so then plus x. Okay, and then I'm going to take the derivative of the derivative. And the derivative of the derivative is 2b2. I know 2b2 is equal to 1 because q2 of 0 is 1. So what is b2? 1/2. So this is a quadratic representation of one of our favorite functions, e to the x. Let's graph it on our calculators just to see what it looks like. Here's an example of a Taylor polynomial. Now it's not centered at 0, right? It's centered at a. So it's been shifted. But conveniently, what would happen if I plug a into x minus a? It would cancel out, right? So conveniently, we'd still be able to do the same process we did before, where we take the derivative and when we plug in a, well, it'll wipe out the other terms other than the first term, and we'll still be able to work through. Do you want to do this one? Okay, yeah, sure. So if I take q2 of a, right? q2 of a, these terms would go away, right? Okay, so I can say that b0 would be 5 if I plug in a, right? q2 of a would be make b0 equal 5. So let's take the derivative of q2. If I took the derivative, that would be b1, and the x minus a would drop off, and then I'd get plus 2b2 times x minus a to the first. So q prime of 2 of a, if I plug in a, I'd get b1, right? And so b1 would have to be equal to 8, right? Because I know q2 prime of a is 8. So now I've got the second piece, the second coefficient. Now the third one, you already know what's coming. What are we going to divide that negative 12 by? By 2. Yep. So watch it happen here. We're going to take q prime of, we're going to take the derivative of q prime. So it'd be q double prime of x. So that would be 2b2. So q double prime of a, of course, won't change anything here because there's no x to plug a into. So then 2b2 would equal negative 12, so b2 would equal negative 6. So now I have my polynomial. That should be, is that b2? Yeah, this should be b1. So b2 should equal negative 6. So I have a polynomial. It's 5 plus 8x minus 6x squared. That would be a polynomial that would represent these clues right here. Okay, so I'm going to skip to the formal proof on this in just a moment here. Okay, so P3 of 0, right? This is a third degree polynomial. That's what this 3 means, here and here and here and here. That just means I'm going to come up with a third degree polynomial representation of some function I don't know. Sweet, that's a lot of unknowns. So if I plug a 0 into this function, what goes away? This and this and this. It's gone, right? It's gone. So A0 equals P3 of 0. Okay. All right, so let's say I took the derivative of said function. Oh, goodness. I took the derivative of said function. Okay. The derivative of this, of course, that'd go away. The x would go away here. This would become 2a, 2x, and this would become 3a to the x squared, right? So if I plug a 0 into that, now what do I have left? A to the first, or a1, right? So a1 is equal to p prime of that polynomial at 0. Okay. Let's keep going another round here. If I were to, oh, I shouldn't have done that. Go back. If I were to then take the next derivative, that would eliminate this term. Those would both be gone. Now the x would disappear, and this would become 2 times 3a3 of x, right? Reduce that power. Okay, so if I plug a 0 into that thing, what do I get? 2a2s, right? 2a2s. So really what I've got is a2 is equal to p double prime of that polynomial divided by 2. Okay, one more time. I'm going to take the derivative of this thing, so this will disappear, and so will this. So p prime of 0 in this case will equal 2 times 3a3, which is equivalent to a3, if I divide by 2 and 3 on both sides, would be p triple prime of 0 divided by 3 times 2. Now, what does this kind of look like? Maybe a factorial, right? It's 6, or 3 times 2. This would be 2 times 1. This would be over 1, and this would be over 1 as well. Well, guess what? This is really just 0 factorial. Yes, 0 factorial is 1. This is just 1 factorial. This is just 2 factorial. And this is just 3 factorial. You can divide by 0 factorial, yes. Let's do the first 3 terms. So any function can be represented with this series, this Maclaurin series centered at 0, by taking p3 of 0, adding p prime 3 of 0 times x, plus p double prime 3 of 0 divided by this 2 factorial thing, plus p triple prime of this third degree polynomial of 0 divided by 3 factorial. Now this 3, right, this 3 right here, and right here, and right here, tells us that we want to stop at the third order derivative. But what if it was an n? What if I change this to an n? Right? That means I don't want to limit myself. Right? I don't want to cut it off after a certain point and say that I can't represent it any further. So what you would do is you'd go out to the nth derivative, right? The nth derivative of this polynomial at 0 times x to the nth over n factorial. Right? We take the nth derivative times x to the n power over n factorial, and that's how we'd represent that. Zero factorial.
It's cool.
Zane is about to prove why 0 factorial is 1.
Okay, so take a normal factorial. So take like 4 factorial, right? 4 factorial can be expressed as 4 times 3 factorial.
Sure. Yep. Yep.
So in any factorial, you can express n factorial is equal to n times quantity of n minus 1 factorial.
Yep.
So 1 factorial. 1 factorial is equal to 1 times 0 factorial. Divide everything by 1. And 0 factorial. Actually, wait, I'll mess that up. So it just simplifies because you take the 1. So 1 factorial is equal to 0 factorial.
Oh.
So they're the same.
1 times something. That's.
Yeah, but that's not.
Yeah, but wouldn't, if we can say these are equivalent, then 1 times something. That's. So either 1 factorial equal 0 factorial equals 1 or 1 factorial equals 0. But it's another familiar function. And I've told you all of the derivatives. And so we know the first term we want to divide by 0 factorial. We want to divide the second one by 1 factorial, then 2 factorial, then 3 factorial, then 4 factorial. Okay. And then I can just throw these numbers in there, right? So here I'm going to have 0. Here I'm going to have 0. Here I'm going to have 0. So what's going to happen to those terms? They're going to go bye-bye. See ya, see ya, see ya. The other ones, I have a positive 1 here, and I have a negative 1 on the third order. The third order has a negative 1. And if I write this as a 5th degree polynomial, this is a representation, believe it or not, of, guess what function we know? What functions do we know go negative 1, 0, 1? Yeah, it is a representation of sine of x. Filthy. So you could go further out. Let's take a gander at what we think the next term would be. Would it be positive or negative? Probably positive. This went from an x to the first to an x to the third. What do you think would be next? X to the 5th over 5 factorial, which is 120, minus x to the 7th over 7 factorial, which is 5040. And the further you go out, the better the representation. Here's the other cool connection. Is sine an even or an odd function? It's an odd function, right? It's an odd function. And guess what? All the powers of the sine polynomial are odd. Guess what all the powers of the cosine function will be? Even. So I could look at the cosine function, and I'd get something very different. It's part of the homework, so you can check it there too. But this would be a polynomial representation of sine x. And you can go as far out as you want. You can make it as accurate as far out as you want to. It's pretty cool. Centered around 0. So we'll talk more about fitting functions tomorrow. Thanks, Zane, for that proof. That was very, very conclusive. Like, subscribe, comment below, and go do some push.